So, um, have you ever had that, like, creeping feeling that the AI you're using today somehow just isn't the exact same AI you were using yesterday?
Oh, yeah, like it's just slightly off somehow.
Exactly. You ask it a question, and it gives you this slightly different flavor of answer, or, maybe it misses a really subtle nuance that it used to catch effortlessly.
Right, and most people just sort of joke about it. They refresh the page, maybe clear their cache, and just move on with their day.
Yeah, but, well, what if that drift isn't just a weird quirk of the cloud? What if it's actually a mathematically proven vulnerability?
It's basically the ultimate modern ghost in the machine. People really think they're just imagining things, but that subtle degradation is a very real, measurable phenomenon.
It's wild.
And honestly, the craziest part of all of this is that the way the tech industry is currently trying to catch that ghost is, well, it's structurally fundamentally flawed.
Which brings us to today. Welcome to this deep dive. We are going on a mission today to unpack this massive slow-motion collision happening between international law, computer science, and, like, the literal silicon sitting inside your devices right now.
Yeah, it's a huge topic.
I went down a serious rabbit hole recently, and it all started with a single six-syllable word buried in an upcoming European law.
Just one word.
One word. And that led to a totally wild 290-page patent application. It's US 19,637,714, and there's massive viral debate breaking out among engineers online. So the mission today is to explore why every single AI software compliance tool currently on the market might be completely invalidated very soon.
Right, and why the only real solution might require fundamentally changing how computer memory actually works from the ground up.
It's such a fascinating collision. You have this incredibly dry regulatory document on one hand,
Yeah.
and then you have these intense debates bringing in quantum physics, Alan Turing, and even the 2008 financial crisis.
Yeah, it covers so much ground. But to set the table here, this deep dive is really about connecting those dots between legal definitions, physical hardware, and the future of AI safety. And it all starts with a ticking clock.
Right, let's talk about that clock. So August 2, 2026.
Yep, that's the big day.
That is the deadline when Article 14 of the EU AI Act goes into full enforcement. And this article, it requires that anyone deploying a high-risk AI system must have the ability to, quote, correctly interpret the high-risk AI system's output.
And the specific mechanism they explicitly demand for that interpretation is, quote, independent verification.
Independent verification.
Yeah.
Which, I mean, on the surface, that sounds like standard, boring compliance jargon.
Oh, totally. You hear that and you instantly think of, like, a guy with a clipboard checking boxes.
Yeah, exactly. But independent isn't just a casual adjective here, right?
No, not at all. It is an incredibly strict legal term. It has 50 years of intense precedent rooted in financial regulation. So if you look at laws like Dodd-Frank or MiFID II or
The
Sarbanes-Oxley.
big financial ones.
Exactly. They had to legally define what independence actually meant after all those massive corporate scandals. And in that legal context, independent means the auditor absolutely cannot share tools. They cannot share office space.
Wow, okay.
And critically, they cannot share failure modes with the entity being audited. They have to exist in a completely separate failure domain.
Okay, let's unpack this idea of a failure domain, because it's vital to the whole argument. So think about a massive bank. It's like letting a bank audit its own vaults using its own internal accountants, running on its own accounting software.
Right, which is a terrible idea.
Right. Because if the bank's accounting software gets hacked, the auditor's report gets hacked too. If the power goes out in the building, both the bank and the auditor go completely blind at the exact same time.
Because they share the exact same failure domain.
Exactly. So if you're listening to this and you're a compliance officer or a CTO or, just someone deploying an embedded AI co-pilot like Microsoft 365 or Salesforce into a corporate environment, this 2026 deadline is a huge deal for you.
A massive deal. Because if your auditor goes down with your ship, you aren't legally independent. You just aren't.
Right. And this is where the legal theory crashes headfirst into computer engineering.
Yeah.
Once you really grasp that legal standard of a separate failure domain, you start to see why independence might actually be an impossible bar for software to clear.
Right, because, well, software doesn't just float in the ether, It lives on a physical chip.
Yeah.
And every single software compliance tool out there right now, whether you're using a sophisticated vector database or ARD filter or RLHF constraint.
Reinforcement learning.
Yeah, exactly. They all run on the exact same silicon substrate as the AI they're supposedly checking.
So they're sharing the same motherboard.
They share the motherboard, they share the memory bus, the cache hierarchy. They are literally living in the exact same house.
Man. Okay, and when we look at the actual mechanics of how software verifies something, it's not magic. It's a sequential multi-step pipeline, right?
Right. Software checking software isn't instantaneous at all. It actually takes 7 steps. It has to fetch the data from the memory, pull it across a physical wire into the processor, compute a mathematical hash,
Okay, that's 3.
then load a stored hash to compare it against, run the actual comparison, branch the logic based on the result, and finally, handle any exceptions and log the acknowledgement.
7 steps. That's a lot of heavy lifting under the hood. So how long does a 7-step pipeline like that actually take to run?
Usually about 5 milliseconds.
5 milliseconds. I mean, to you and me, that's literally less than the blink of an eye.
Oh, to us, sure, it's nothing. But in processor time, a 5 millisecond window is an absolute eternity. You can have billions of operations occur in that span.
Wow.
And that creates a vulnerability window. During those 5 milliseconds, the checking software is running on the very same hardware as the AI.
Ah, so it's subject to the same physical issues.
Exactly. The same memory displacements, the same voltage fluctuations, cosmic ray bit flips, whatever. The checker can drift just like the AI it's actively trying to check.
It's like someone completely rearranging the folders in your filing cabinet while you're busy blinking.
That's a perfect way to put it.
Which takes us all the way back to 1936, to this concept called the Turing Trap. Alan Turing mathematically proved that software cannot definitively audit software. It's like a foundational rule of computer science.
Yeah, the halting problem. If a computer program tries to determine if another program is doing what it's supposed to do, it basically gets stuck in an infinite regress.
Right, because you need a checking program for the checking program.
Yep, and then another checker for that one, forever and ever.
And this specific paradox is what caused such an explosion in that viral LinkedIn debate we looked at.
Yeah.
It's incredibly polarizing. You have these brilliant software engineers who have spent their entire careers building state-of-the-art verification tools.
And suddenly, someone is pointing out that the fundamental math says those tools can never be truly independent.
Right. So you had professionals stepping in like Ted Bouskill, arguing that Turing's halting problem doesn't actually invalidate modern formal software verification.
Yeah, his argument was essentially, hey, if Turing's proof meant software couldn't check software, then things like code compilers and automated test suites would be logically impossible.
Which they obviously aren't. And then another perspective came from Russell Parrott. He was looking at it from the policy side, arguing that Article 14 of the EU AI Act isn't about computational physics at all.
Right, he argued it's purely about human oversight. The idea that as long as a human can pull the plug or override the system, compliance is met. So he was saying this whole software compliance is impossible thing is just a massive misread of the regulation.
Yeah, and we should be clear, we aren't taking sides here, just reporting what the sources say, but those are very common pushbacks in the industry right now.
Very common. But Elias Moosman, who authored the essays and that 290-page patent application we're looking at, he countered those points head-on.
Right. What was his argument?
So Moosman argues that the issue isn't about verifying a static sleeping code on a hard drive, which is basically what a compiler or a test suite does. The issue is what he calls runtime functional role continuity.
Okay. Runtime functional role continuity. That's a mouthful. Let's break that down into plain English.
Sure. It basically boils down to this. Is the entity producing the output right now, at this exact millisecond, still the exact same entity you authorized an hour ago?
Oh, okay.
Because in a computer, data is constantly moving in and out of temporary memory. If that data silently displaces, like if the correct piece of data is suddenly shoved into the wrong physical location in the memory bank, the functional role of that AI has essentially drifted.
So, addressing the human oversight argument from Parrott.
Yeah, Moosman's point is that if the AI's identity has silently mutated in the memory, the human is now overseeing an entity they never actually authorized in the first place.
Wow. Okay, let me just play devil's advocate for a second, thinking about the listener who might be at a company spending fortunes on this stuff.
Go for it.
Even if I spend like $10 million building the most top-tier, state-of-the-art AI safety filter in the world, this argument suggests it might be legally useless for compliance.
Under this interpretation, yes.
Because the filter lives in the same house as the AI. So if the memory of the AI shifts, the memory of the filter can shift right along with it during that 5-millisecond window.
Exactly. Under the strict legal definition of a separate failure domain, that filter simply fails the independence test. If the auditor and the AI share the exact same vulnerability window, it isn't an independent audit.
It's just the AI system self-reporting its own health with extra steps.
Bingo.
So software is completely trapped in this house of mirrors, which means the only way out is to go down to the foundation of the house itself, right? You have to solve this in the physical hardware.
Yeah, when software checking software creates an infinite loop, the only way to break the loop is to step entirely outside of it.
And this is where we get into the proposed fix, this patent application for a new architecture called SPH.
Right. SPH stands for semantic meaning equals physical position equals hash address.
Okay, so let's use an analogy to understand how a normal computer memory works today. It's essentially like a giant parking garage.
A very fast parking garage, but yeah.
Right, and the computer's memory address is just the number painted on the parking spot.
Yeah.
It tells the computer where to park the data, but it tells you absolutely nothing about what is actually parked there.
Exactly. A Honda Civic could be in spot 42, or a massive Ford truck could be in spot 42. The software actually has to walk all the way over to spot 42, look at the car, and run a check to figure out what it is.
And that walking over and checking, that separation between the address and the identity, that's what causes that 5-millisecond window, right?
Yes, that decoupling is exactly why software requires that window to fetch and verify. But SPH completely changes that relationship. It makes the physical position in the silicon deterministic.
What does that mean in practice?
It means the actual semantic meaning of the data dictates exactly where it physically sits in the hardware.
Oh, wow. So going back to the parking garage analogy, it's like a parking lot where spot 42 is physically molded to the exact atomic shape of your specific Honda Civic.
Yes, nothing else can physically fit in that spot.
So if a car is successfully parked in spot 42, it must be your Honda Civic. You don't have to walk over and check the license plate. The physical location itself proves the identity.
That is the perfect way to visualize it. The physical position guarantees the semantic meaning. And the way the hardware actually executes this is through a specific command called a compare and swap instruction, or CAS.
A CES, okay, how does that work?
Well, unlike a long software script, this happens in one single indivisible tick of the processor. On a modern Intel Xeon chip, a CAS instruction takes about 5 nanoseconds.
Wait, really? We were talking about 5 milliseconds earlier for software. This is 5 nanoseconds.
Nanoseconds, yeah. So the vulnerability window effectively drops to 0.
Because the fetch is the verification.
Exactly. The moment the data drops into the hardware slot, it's verified by the physics of the silicon itself. There's no temporal gap for the data to drift.
That is incredible.
And this mechanism generates a cryptographic trust artifact right from the hardware. You get an RC score, which measures the structural certainty of the data. You get a tamper-proof hardware timestamp, a TSC. And you get a binary pass or fail.
So it isn't some probabilistic guess from a software model.
No, it's a definitive yes or no from the laws of physics.
What I find so elegant about this is how it totally escapes the Turing Trap. Because software gets stuck in an infinite regress because it's what we call Turing-complete.
Right, it can run complex logic, make branching decisions, and get stuck in those infinite loops.
Right, but the physical logic gates executing this CAS instruction are not Turing-complete. They're just physical pathways for electricity. They are literally physically incapable of looping or drifting.
And the interesting thing is, policymakers are actually starting to realize this. In that same LinkedIn thread discussing the EU AI Act, a governance consultant named Basil C. Puglisi brought up a very revealing parallel in U.S. legislation.
Really? What's happening in the U.S.?
There's a proposed bill called the Verified AI Inference Standards Act, or VAISA. And VAISA actually mandates hardware-signed attestation before regulated data can cross boundaries.
So we have the European Union writing Article 14 and the United States drafting VAISA, and both are organically converging on the exact same physical requirement for AI safety.
Completely independently of one another.
That's wild. The law is essentially realizing that software is just too squishy, and it's starting to demand physics instead.
Yeah, which brings up a very logical counter-argument that people have. If AI safety is really this critical, why don't the massive tech giants just build bigger dashboards?
Right, like we pour billions of dollars into observability tools. It feels like we should just be able to watch the AI really, really closely using telemetry and surveillance. Why go through the incredible expense of inventing a totally new memory architecture?
Well, we have to remember what surveillance actually is in this context. Surveillance is just more software observing software.
Right. It's the bank auditing the bank again.
Exactly. It suffers from the exact same substrate vulnerability. You cannot use a system to definitively audit itself. The sources draw this brilliant, kind of terrifying parallel to the 2008 financial crisis to explain this.
Oh, the ratings agency.
Yes. Think about what happened in 2008. The ratings agencies were acting as the surveillance mechanism for the entire financial system. But they were running their risk models on the exact same data the banks provided.
The surveillance was built on the failing substrate.
Yep. The audit trails, the software, the reports, they all confirmed everything was perfectly solvent and healthy, right up until the very morning the entire global system collapsed.
Because the surveillance couldn't detect the failure since it shared the failure mode.
Yeah.
Man, that shared failure mode has massive real-world consequences today.
Oh, huge consequences.
And here's a statistic from the deep dive that absolutely floored me. The global AI liability insurance market is currently sitting at $0. Zero.
It's true, and it makes sense when you think about it. Insurance carriers are entirely data-driven. They write policies based on actuarial data and mathematical risk. They simply cannot underwrite a risk that they cannot objectively measure.
Because AI software shares a substrate with its own verification tools, there's no reliable actuarial data.
Exactly. How do you price the risk of an AI system mutating if the tool measuring the mutation might literally be mutating right alongside it?
It's a paradox. So we're pouring $8.5 trillion into AI infrastructure globally. We're embedding it into hospitals, power grids, financial markets, but the insurance industry won't touch AI liability with a 10-foot pole because nobody can actually prove what the AI is doing at runtime.
But the moment a hardware measurement exists, like the one proposed in this SPH architecture, that market constraint completely vanishes.
Which would be huge.
Oh, yeah. The analysis compares this future explosion to what happened with cyber insurance. Between 2015 and 2025, cyber insurance grew from a $2 billion niche to a $14 billion industry.
Wow. And that didn't happen because cyber attacks went away, obviously.
No, it happened because carriers finally acquired the tools to physically measure network risk. Once hardware can physically guarantee an AI's functional role, the AI liability market is going to follow that exact same trajectory.
I want to zoom out and look at the macro picture here because there is this massive philosophical insight hidden in the sources about why we're in this situation in the first place. Like, why is AI alignment and safety so underfunded and controversial compared to other historical challenges?
It comes down to a concept the sources call structural gravity. They reference Carl Sagan, actually.
Charles Sagan.
Yeah, he once gave a famous speech pointing out that the United States happily spent $10 trillion on the Cold War, but basically ignored the existential threat of climate change. He called it a tragic double standard.
Right.
But the argument made in these essays is that Sagan was actually wrong about the why. It wasn't a double standard at all. Large systems and structures consistently allocate capital toward things that preserve their own momentum and continuity.
Right, like the $10 trillion spent on the Cold War didn't just buy missiles. It built the modern aerospace industry, global supply chains, massive research universities. It funded the rapid expansion of the very power structure making the funding decisions.
Exactly. Whereas climate change mitigation asks those existing power structures to dismantle themselves, or at least significantly slow down their consumption.
When you apply that to AI, you see exactly why alignment struggles for funding. When people argue for AI safety, they almost always ask the tech ecosystem to pause, to establish moratoriums, to slow down.
Yeah, they're asking a multi-trillion-dollar structure to act against its own momentum. So naturally, the structure ignores the request. A massive structure will always decline a request to fund its own deceleration.
That makes so much sense.
Yeah.
But this hardware patent, it doesn't ask for a pause. The essays explicitly call this SPH technology a steering column.
The steering column, right. It doesn't ask the AI industry to hit the brakes. It gives the structure the ability to verify itself while continuing to move forward at full speed. It offers a safety solution that actually protects the bottom line instead of threatening it.
And that steering column is necessary because trust in these systems physically decays over time. There's this fascinating thermodynamic metric mentioned in the documents called the crossing tax.
Yeah, the trust decay is quantified at a rate of KE equals 0.00003 bits per boundary crossing.
Okay, let's define a boundary crossing. What does that actually look like inside a computer?
Well, every time data moves, it crosses a boundary. If data moves from a server in Virginia to your laptop in London, that's obviously a boundary crossing.
Sure.
But even on a micro level, if data just moves from the RAM stick to the CPU cache on your motherboard, it crosses a boundary. And every single time that movement happens, thermodynamic noise is introduced.
So based on that 0.003-bit decay rate, trust in a system have a half-life of 231 crossings.
Exactly. And that isn't some software guess. It's a literal thermodynamic measurement of the physical rate at which a system loses its original structural identity.
Which introduces what the sources call pre-existential risk. When we talk about AI risk, people always jump straight to the sci-fi scenarios. The Terminator robots, the AI turning evil and launching weapons.
But the real danger is much, much quieter than that. The real danger is the silent, gradual loss of our own decision-making capacity.
Yeah.
It happens when the AI's functional role drifts so slowly that we don't even notice. The internal logic shifts. Peter silently becomes Paul. But the system still trusts Paul because the software checker also drifted and confirmed that everything is fine.
So the ultimate catastrophe isn't the failure of the AI itself. The catastrophe is the loss of the instrument that could have warned us about the failure.
Exactly.
Think about the implications of that for a second. You rely on these embedded systems every single day to make decisions for you. They sort your emails, filter your news, analyze your company's financial data, route traffic.
Right, they're everywhere.
If the system's identity slowly mutates, and you have no physical way to measure that mutation, you are literally handing over your sovereignty to a stranger. You're losing the basic ability to know who or what is actually making the decisions in your life.
That is why the distinction between software verification and hardware verification is not just technical pedantry, it's critical to maintaining human agency. Without physical hardware enforcing that boundary, your oversight is just an illusion.
It's a hallucination generated by the very system you're trying to oversee.
Exactly.
Let's distill the journey we've just been on today. We started with a single legal requirement, independent verification, written into Article 14 of the EU AI Act.
Yep.
We followed that requirement down into the 5-nanosecond atomic ticks of the silicon chip, exploring how a memory architecture like SPH is required to escape the infinite loop of the Turing Trap.
And then we zoomed all the way back up to the macroeconomics of an $8.5 trillion industry, understanding why hardware physics is the key to unlocking AI liability insurance.
And the core takeaway across all of this is really striking. Software alone is completely incapable of regulating AI. True verification, the kind that can satisfy international law and unlock actual actuarial trust, must be anchored in the physics of the hardware itself.
It really requires a fundamental shift in how we build the physical foundation of computing.
Which leaves us with one final, incredibly provocative thought from the deep dive. Buried in the documentation, there is a mention of a spatial tile game called Tesseract.nu.
Right, I saw that.
It was designed to let people physically interact with this kind of SPH coordinate system. And the claim is that when players submit a definition that perfectly aligns with its highest believability coordinate in the game, they physically feel the cache hit of verification.
They experience a visceral physical sensation when meaning and physical position perfectly align in the hardware.
It creates a literal alignment between human intention and physical reality.
It's a wild concept.
It really is. So as AI becomes completely invisibly woven into the fabric of our lives, what if the future of trust isn't a signed legal document? What if it isn't a fancy observability dashboard or a 500-page compliance report that some lawyer reads?
What if the ultimate proof of an AI's safety is something you will literally have to feel in the hardware of your device?
Keep questioning the physical substrates of the technology you use every day, because the ghost in the machine might just be the machine itself.